Hello, this is Mrs. Taylor, and I'm going to introduce you to the washer method using an excerpt from Master the AP Calculus A, B, and BC Test written by Michael Kelly. It's an excellent book. In that book, it states that the washer method, you use it to get the rotational volume of the area bounded by two functions, f of x and g of x, on the interval a to b if f of x is greater than or equal to g of x on the interval a to b. And that volume is given by the b equals pi times the integral from a to b of capital Rx squared minus lowercase rx squared times dx. And the capital R represents the outer radius, the lowercase r represents the inner radius. And so this is a very official definition, and basically my unofficial way of thinking about it is to write it this way, where it's basically the same as the disk method. It's still based on pi r squared h. It's just now your slices, when you slice your salad, are still circular discs, but they have a hole in the middle. So that's why it's called the washer method. And to accommodate for that hole in the middle of your cross section, we subtract the outer radius and the inner radius as part of our integral. And so what this would look like in the context of a problem is if I had something like this. It says find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. And so we have y equals x, y equals 1, and x equals 0. So I'm going to graph y equals x. And once I have that graphed, I'm also going to include my two other curves that are bounding my area. So y equals 1, that will be a horizontal line passing through 1 on the y-axis. And then x equals 0, that's a vertical line passing through 0 on the x-axis, which is basically the y-axis. And so if I'm just looking at the region bounded by those three lines, it's this little tiny region here. Take a snapshot of that and make that bigger. And so my region is actually really small. It's just inside of here. And so I'm going to rotate that region around the x-axis. Like that here. And what's going to happen is once I rotate it, I'm going to get a mirror image over here of these two lines. And so the other half is going to look something like this. And so if I sliced this to make my discs, I'm going to get this hole in the middle of each slice due to this gap here between these two lines. And so that's why it's a washer method and not a disk method problem. So our volume will still be V equals pi and then times the integral. And we are still looking for limits of integration just like with the disk method. And so we're integrating in terms of x because we're rotating around a horizontal line. So these two lines here, they intersect at 1 and 0. So those are my limits of integration. 0 to 1. And then I need to determine my outer radius and my inner radius. So outer radius is the curve that's farthest from my axis of rotation. So looking at this diagram, if I'm starting in my axis, the line that's farthest away is this horizontal line here, which is y equals 1. So that's my outer radius. So that would be 1. And don't forget to square your radius. And then minus your inner radius squared. Well, the inner radius is from my axis of rotation to the closest curve. This will be the radius of the hole inside each disc, the hole inside the washer. And so You could think of these as top minus bottom, but our bottom is the axis, the x-axis, so it's just 0. Don't really have to write that in there, but keep that in mind for more complicated problems. The inner radius would be the distance from our axis of rotation to the curve y equals x. So inner radius would just be x squared. So then I have my integral all set up. I can simplify and integrate. So simplifying 1 squared would just be 1. So when I integrate that, I get x. And then simplifying x squared, well, that's just x squared. And so when I integrate that, I get x cubed over 3. And then I evaluate from 1 to 0. If I plug in 0, I get 0. So I'm just plugging in the 1. So that would be 1 minus 1/3. And again, with free response, we can just leave it like that. And so I'm going to do that. And so that would be the volume of the solid created by this region using the washer method.